Okay, so now it's 4:10 p.m. So, so I'd like to first introduce today's colloquium speaker, Professor Amir Yacoby. So he's a professor of physics at Harvard. Also, he has a Canadian connection. He's a visiting professor and also Lajal Reddy's chair in physics at the Institute for Quantum Computing in Waterloo. Amir has a very interesting educational background. So he received a bachelor's degree in aeronautical engineering. And he was a theoretical physicist after that. Then he decided that all these things are very boring. So he decided to become an experimentalist. He got his PhD at the Weizmann Institute of Science. This is the place I call Weizmann Institute. There are so many wise people there. Then he moved to Bell Labs, and that's the place where I met him. That's like 26 years ago. It's a long time, isn't it? So, and he was a faculty member at Weizmann Institute, but Weizmann couldn't keep him for too long. So then he moved to Harvard at 2006, and he has been there since. He's famous for doing a very difficult experiment, especially like designing it's like hard to do experiment for some very important issues. For example, he was one of the first people who observed the signatures of spin charge separation in a one-dimensional quantum wire. And he also developed novel electron charge imaging techniques. After he joined Harvard, he has been working on applications of quantum information technology to condensed matter systems. So I think today's talk is one of those many efforts. So he invested quite heavily on the possible platform for quantum computation. I think that's the connection that he made with this IQC at the University of Waterloo. Okay, so with that introduction, I'd like to introduce Amir. Please go ahead.
Thank you very, very much, Young Beck. So first, let me thank Young Beck for inviting me, giving me this opportunity to tell you a bit about the work that we've been doing over the past several years. And indeed, this work follows very much the spirit of what Young Beck mentioned, and that is the working at the interface between instrumentation, the development of new measurement capabilities, and the discoveries that can be made with new measurement approaches, new ways of looking at matter. And you might ask yourself, well, we have a tremendous set of measurement capabilities already. Why do we need more tools in order to look at matter? Why is it not enough? And so what I'd like to do, I'd like to start by giving a broad introduction that gives just a few examples from the past decade or so of how condensed matter is really challenging us experimentalists in terms of concepts and predictions that still to a large degree even await confirmation, and partly because the tools that we have are insufficient in order to directly address some of the underlying physics that's going on in these systems. So, and just remember, these are a handful of examples. By no means this is something that covers the entire space. So just thinking about ground state properties, here up on the right, I'm showing what is known to be a quantum spin Hall insulator. It's a two-dimensional system where electrons in principle can only reside in a plane. And if this is a quantum spin Hall insulator, then it turns out that in the bulk of this layer, there are no conducting states, but there are conducting states that live at the edges. And these consist of current carrying edge states that are counter-propagating. In each edge, there are counter-propagating states. But the interesting thing is that the forward-moving electrons have one spin orientation, and the backward-moving electrons on the same edge has the opposite spin orientation. So obviously, if you ask, well, what is the net current flowing along the edge? That is 0. But if you think about what the spin is doing, well, the spin actually is opposite in each direction, which means that there is a net spin current. And this is a very simple observation that should exist in a quantum spin Hall insulator. And yet we don't have any way of measuring spin currents, especially not in equilibrium. And so just knowing that this state exists requires very indirect observations, but this simple direct one, we don't have a tool to do that. Another example of a challenge that we're facing in the ground state properties of materials is shown here on the bottom left. This is an image from our group. You see the pink here is basically a monolayer of graphene. And when graphene, it turns out, subject to strong magnetic field, when its density is 0, it favors a ground state, which you see here in the inset, which is an antiferromagnet. It is slightly canted, namely the magnetic field is out of the plane. The spins are mostly pointing in the plane, and they're canted out of the plane. And the underlying reason for this antiferromagnetic state is very interesting and fundamental, and I'm not going to spend time here about it, but I just want to emphasize that while we do have tools that enable us to know that materials are ferromagnetic or antiferromagnetic, for example, neutron scattering, these techniques do not apply for this particular system because the volume of spins here is tiny. It's a monolayer, and the density of spins, because this is a semiconductor, is roughly 1 part in a million, smaller than what you'd find in a conventional antiferromagnet. And so the sensitivity of existing techniques simply to determine, hey, this is an antiferromagnetic state, doesn't exist. We can go beyond the elementary, the ground state of properties and talk about excitations. So now we can ask, well, okay, suppose I have a ground state, but what if I inject some energy into the system in the form of some excitations? What are the nature of these excitations? And here again, the past decade or so has presented us with really interesting excitations of interesting systems. And these are, for example, the spin liquid, in which the excitations consist of spin-carrying particles that turn out to be fermionic. They carry no charge. And it would be really nice to be able to have some measurement technique that tells us, hey, this system has excitations that consist of spin with no charge. Unfortunately, again, we have a lot of tools that are allowing us to do transport measurement, electrical transport measurement, but not so much the investigation of spin excitations. On the bottom left, I show another type of interesting excitations, and that is the excitations that might exist in a topological superconductor. These could be non-abelian excitations, and again, our tool set is insufficient currently to really tackle these two problems in a very effective manner. Now, if I have some excitations, and these excitations are long-lived, I can ask, well, what about their transport? Can I define a chemical potential for these excitations? Can I create gradients of chemical potential to drive currents of these excitations, etc.? And the answer, of course, is yes. There are some really interesting predictions about a variety of these things. So up here on the right, you see predictions about the excitations of regular magnets, actually, which behave as a superfluid. And I'll talk a little bit more about this later on in this talk, where basically you can create a situation where a current of spin, basically angular momentum, can propagate over very, very long distance with very little dissipation. Alternatively, in the spin liquid system, where you have very bizarre excitations, these spin-ons and even non-abelian excitations, one expects some interesting properties of heat flow through these excitations. These excitations carry energy, so it's this transport of energy, and that energy transport should be quantized. So overall, what I tried to do in this kind of few minutes introduction is to give you a sense that although we do have a large set of measurement techniques, we really should not rest and constantly strive to develop new ways of measuring physical phenomena, because they would give us new insights into the properties of complex materials. And really, this is what has defined my group activities over the past several decades, where we are really constantly developing new measurement techniques, new apparatus, new instrumentation, new concepts for measurements, and then using them in order to explore materials. And the talk today will thread basically the same interface between instrumentation and what we can do with it. And I'm going to give a few examples without going too much into details into this. So for today's talk, I'm going to be describing a measurement technique that uses a quantum bit, basically a spin quantum bit. It's an atomic defect. I'll talk more about it, that allows us to measure magnetic fields locally. And what I'd like to show is that while the sensor sounds really simple, it measures magnetic field locally. By knowing certain chapters in physics that connects magnetic field to the underlying physical phenomena we're interested in, we can access really novel properties. And specifically, we'll be able to access these properties on nanometer scales. The challenge of mesoscopic samples that I mentioned before are less of a problem when you have a local probe that is extremely sensitive. It does allow us to look at excitations, not only ground state properties, and look at transport of various phenomena. I'll give just one example of electrical transport in this case, but a different way of looking at electrical transport. So if there's perhaps one message that I'd like to carry out from this talk, is the fact that, yes, we are now thinking about this sensor, and it's a very local sensor measuring magnetic fields. In fact, magnetic fields is a function of frequency we can extract. But it allows us, by knowing the physics that connects this magnetic field to various phenomena, it allows us to study the underlying physics of very different phenomena. And here are just kind of an array of examples. One is, we can study, for example, image in real space spin density of paramagnetic spins. So these are just fluctuating, unordered spins. But using this local magnetic field sensor, we can actually reconstruct, just like a magnetic resonance imaging tool reconstructs the density of spins in our body. We can do this, but this time with nanometer spatial resolution and with single spin sensitivity. Perhaps a more classical example is the problem of measuring magnetization. And we know that there is a kind of simple connections between magnetization and magnetic field. And if I know the magnetization, I will know what the magnetic field pattern that I will get in space. But it turns out that the inverse problem is really hard. In fact, it's not determined even. There could be an infinite set of magnetizations that produce precisely the same magnetic field pattern that I would measure outside the material. And so this example was a tour de force to basically use other physics ingredients to be able to invert the property of magnetic field to magnetization in these skyrmion textures that exist. They look like hedgehogs. This is kind of an image of the measured magnetization texture of one of these skyrmions. The bottom three windows here is what I'll be talking about today. I will be talking a little bit about the measurement of spin chemical potential. I'll explain what it is and how it's related to the property of spin superfluidity. I'll talk a little bit about imaging electrical transport using this local magnetic field sensor. And lastly, I'll describe a new scattering platform that uses spin waves as the particles that scatter off a novel medium, and the use of our magnetic field sensor in order to image these scattering patterns in real space. All right, so let me just, I'm sure you've heard several talks about NV centers. I'm going to just remind you briefly the important features of it that are relevant for today's talk. So number one, it's a defect. It's atomically sized. And this basically sets the spatial resolution. It means that we can measure magnetic field in principle down to the atomic scale. It consists of a nitrogen substitution and a missing carbon atom. It's this hybrid defect that has a spin triplet characteristics. And its level diagram is shown down here as a function of magnetic field. Since it's a triplet, there's 3 levels, the ms equals 0 state, ms equals -1, and ms equals +1. And they depend on magnetic field in a well-predicted manner. Basically, the G factor of this defect is 2. So we know the slope of these lines. And you can already see that the way to measure a magnetic field, for example, is to shine some microwaves that tries to take the system from one state to the other. And by finding the frequency that drives the system, we know what the magnetic field is. One key ingredient of this system is that we can detect whether this defect is in its ground state or in one of its excited states simply by shining some light on it and looking at fluorescence. It turns out that it fluoresces more if it's in its ground state, and it's dimmer when it's in one of the excited states. So this allows us to determine, after we've done our measurements, to read out this spin quantum bit and determine what its state is. This is diamond, so it doesn't care about temperature. This technique works from well above room temperature all the way down to very low temperature, so it's very convenient. We don't need to adjust our technique as we're varying temperatures. And while the defect itself is atomic in size, typically our limited spatial resolution will be set by the distance of our sensor from the material of interest. This is not always the case, but for the purpose of today's talk, this will be the case. So how do we use this defect as a magnetic field, a sensitive magnetic sensor, or as a quantum sensor? So in order to have a, to have a quantum sensor, there are basically 3 ingredients that are needed. This is a 2-level system, so all possible superpositions of this 2-level system. And when I say 2-level system, I'm referring to the fact that I'm only going to be working with 2 of the levels, the ground state and let's say the ms equals -1, and we're going to ignore the ms equals +1 state. So all possible superpositions of the 0 and 1 state of this 2-level system are plotted here on this block sphere. The ingredients that are needed are a mechanism to initialize it in a reliable way, and that's done by shining green light. It prepares this defect in its ground state, in the 0 state. We need to be able to control it, namely to form arbitrary superpositions of this defect. And finally, as I mentioned, by fluorescence, we can detect its state, its projection onto the axis, either 0 or 1. And 0 is the ms equals 0 state, 1 is the ms equals +1 or -1 state, one or the other. So the way we use this as a sensor is by initializing along the North Pole in the ground state, and then we'll apply what's called a pi/2 pulse and tilt this spin into the equator, and let it evolve under the influence of a magnetic field of interest. What this does is it precesses this spinner, acquires a phase. And of course, the maximum phase that we can acquire is dependent on the coherence or the lifetime of this 2-level system. If we wait too long, the information is going to be lost. So therefore, the maximum phase is going to be given by the external field that we're interested in times some coherence time. And that's going to be the signal. We can now estimate what the noise is. The noise is, because this is a quantum projected measurement, each measurement is going to have an uncertainty of pi in the phase. But we can improve upon that by repeated measurements. This is the standard error limit. And so we can now compare the signal to the noise, and we arrive at a very simple criterion for what is the sensitivity of this sensor. It's given roughly by 1 over the coherence time and 1 over the square root of the number of measurements that we can do in a unit of time. And here we're going to look at 1 second of integration. That's usually how you define sensitivities. And if I were to plug in numbers for the quantities that we know for our typical nitrogen vacancy centers, the typical sensitivity that you get for magnetic field is on the order of 10 nanotesla for 1 second of integration. I'd like to give you just a sense of whether this is kind of good or bad. So if I have 1 electron spin, so 1 Bohr magneton, and I'm looking at the magnetic field it's generating a distance 10 nanometers away, it's producing 1 microtesla, so about 100 times more than this magnetic field sensitivity. If I had a nuclear spin and I'm sitting 10 nanometers away, it produces 1 nanotesla, so not enough maybe to measure a single nuclear spin with this simple protocol. There are better protocols that I'm not going to describe today. But this is pretty good in terms of sensitivity. Now, so far I've described how we would measure a static magnetic field, but what about some alternating magnetic fields or noise in magnetic field? Well, it turns out that this is what makes this sensor so versatile, is that we can apply protocols, pulses, that control the state of this defect as a function of time in very sophisticated ways, in such a way that depending on the sequence of pulses that we apply, we can filter out different sectors of the signal magnetic field versus frequency. So if I have a system that has some spectrum of magnetic field versus frequency that it's producing, I could basically choose a pulse sequence that isolates various sectors of this spectrum, and I could really study the entire spectrum with high precision in a range of frequencies that's all the way from DC to several tens of gigahertz. So that's how this sensor works. How does it look? So we've been developing these platforms for the past almost decade now. What you can see here at the bottom is a piece of diamond that used to be a bulk crystal that we have fabricated, carved, and etched away and removed material to form a slab with a pillar sticking at the end. This pillar is not stuck at the bottom, it's actually part of the same crystal. And at the end of this pillar sits 1 defect, 1 NV center. It's about 10 nanometers from the surface. And the pillar itself is used both as an atomic force microscope, basically the lowest point in the experiment that we could use to scan and figure out where we are, but also as an optical waveguide to collect light, because the way we determine the state, as I mentioned, is by collecting light. Recently, we've gone to different type of probes. Instead of these thin slabs, we have now these very thick slabs, and you can see at the end of this slab, 1 pillar. Again, at the end of this pillar, there's 1 defect. And now we can even control the taper of this pillar in a very precise way that allows us to collect optimally the amount of photons that are emitted from this detector. And lastly, we're now integrating also the RF signals that we need in order to control and pulse this defect in order to isolate the various frequency sectors that we might be interested in. All right, so we have this technique. It's capable of measuring magnetic fields as a function of frequency. What can we do with it? So what might be some interesting problems? And the first example that I'd like to give is the measurement of spin chemical potential. And I already introduced the notion of spin superfluidity in the beginning, where conventional magnets, it turns out, could form a state in which the system behaves as a spin superfluid, and it can carry spin currents over large distances without dissipation. Now, this might sound like a very recent topic, but in fact, there's a seminal paper over 50 years ago from Bert Halperin and Pierre Hohenberg. Their title is Hydrodynamic Theory of Spin Waves. And in the first sentence of their abstract, they write, a hydrodynamic theory of spin waves is developed for certain magnetic systems in analogy with the derivation of 2-fluid hydrodynamics for liquid helium. So they already understood that simple magnetic systems will behave very much like liquid helium. But it's really taken the field a very long time to be able to develop the proper tools in order to start addressing questions associated with this kind of superfluid state of the spin excitations. So where is this coming from? Well, the simple answer is that the spin excitations in a magnet are bosons. And if they're long-lived, and certain magnetic systems, if the spin-orbit interaction is very weak, spin is a good conserved quantity, angular momentum is conserved, then the spectrum of excitation in the system consists of these spin excitations. If there is some anisotropy in the system, there will be a gap in the spectrum of these spin waves. And this gap in the spectrum can also be induced by a magnetic field that forms the anisotropy. So what I'm showing here is that if one, at some fixed magnetic field, there's a spin gap up to some energy, and beyond that, we have the possibility of exciting spin waves whose wavelength is very long at the bottom and then becomes shorter and shorter as you go to higher and higher energies. And this spin gap, its dependence on magnetic field is known as the Kittel law. It has this square root singularity that you see here. So anywhere below this blue line, there are no spin excitations, and above, the system has the ability to be excited with spin waves. Now, since these are bosons, we can ask, well, what are some of the salient features of a bosonic system? And of course, one of them is Bose-Einstein condensation. So we could ask, well, suppose I had a way to measure the chemical potential of these spin excitations as a function of the number of excitations. The thing that we know about a Bose-Einstein condensate is that the chemical potential will rise and rise and rise until it hits the bottom of the possible excitation spectrum, and then macroscopic occupation of the ground state will occur. The system will develop an order parameter and will have a macroscopic occupation of the ground state. So we were intrigued by this notion, and we asked ourselves, well, how can we measure this spin chemical potential in a magnet? So one thing to remember is that these spin excitations that exist inside the magnet, they're generating magnetic field noise. These are basically fluctuating spins. And so they're generating magnetic field noise outside of the sample. And we know how to measure this noise because we have a magnetic field sensor that can isolate very precisely sectors of the magnetic field spectrum. And it turns out that if you do a measurement of the rate of equilibration, what this noise does to the two-level system, it causes relaxation. And if you measure that rate of relaxation when the system is in equilibrium, namely the number of spin waves in the system is set only by temperature, versus the rate of equilibration when the system is driven to have more, namely the chemical potential is pushed up, the chemical potential is simply given by this very, very simple formula, where we have two measurement quantities that we know how to measure and a known quantity, which is the energy level splitting of the sensor, the NB center. And when we do this measurement, what we find indeed is that for different magnetic fields, this chemical potential rises as we increase the number of excitation, but then it saturates, and it saturates precisely at the chemical potential that corresponds to the band bottom, where macroscopic occupation now starts to occur. So this was a great, beautiful example of how we can measure spin chemical potential. This has now been used by other groups to measure gradients in spin chemical potential and to extract real spin transport across a system where the driven force is a gradient in chemical potential rather than a gradient in electrochemical potential, which is what drives charge. The second example that I'd like to give, again, is about a different connection between magnetic field and a physical phenomena, and this time it's going to be about electrical transport. So what can be interesting about electrical transport? So what we're familiar with from kind of elementary condensed matter physics, that when we describe the resistance of a material or the conductance, we're mostly thinking about electrons behaving almost as independent particles. And what they're doing inside the crystal is that they're scattering off of impurities or off of phonons. They're basically constantly losing their momentum as they're moving across. And this is very natural to expect in a system that has a relatively large number of impurities, disorder. The mean free path is not that long. And here, what I write is that the momentum relaxation time scale is much shorter than the time scale that it takes two electrons to interact one with the other. This is the conventional Drude model that we all know and like. But suppose we have a very, very clean system, a system where the number of impurities in the system is very small. And so overall, the electrons are interacting with one another much more than they're interacting with other degrees of freedom, like impurities or phonons. And this means that if I look at the electron system as a whole, the energy and momentum of each individual electron is not conserved, but the energy and momentum of the collective, of the collection of electrons, is conserved. And this leads to universal behavior, which is known as hydrodynamics. It's basically underlies the conservation of the collective properties of this system, energy and momentum. And it's something that actually we're quite familiar with and connected very nicely to my bachelor degree in aeronautical engineering, where I studied Navier-Stokes equations there, describing precisely what happens to a fluid when the interaction between the intrinsic interaction between molecules is very strong and there is nothing else. So the overall energy and momentum of the fluid is conserved, even though the energy and momentum of the constituents of the fluid is not conserved. So the question is, where might we find this hydrodynamic behavior and what might be its signatures? So number one, if we want to maximize the interaction between electrons relative to other degrees of freedom, it turns out that going to low carrier system is the right way to go, because the rate of interaction becomes longer, the interaction between electrons becomes faster and faster the smaller the density of the system is. So in metallic systems where the Fermi energy is very, very large, it's kind of unlikely to expect hydrodynamic behavior, but in a semiconducting system, maybe. And there's been some very beautiful transport experiments that were strongly suggestive of hydrodynamic behavior coming out from various groups in Europe, for example. And they were able to measure the characteristic viscosity of the electrons that modifies the conventional transport equation. So normally we have the average velocity of the electrons is given by the electric field. Now we have some additional term that depends on the shear, on the gradients in velocity in the system that causes, that contributes to the electrical flow. Now, one thing we know from aerodynamics or fluid dynamics is that when you send a fluid that's behaving hydrodynamically inside a pipe, the velocity on the boundary of the fluid goes to 0 and it maximizes in the middle. It shows this kind of parabolic velocity profile across the channel. And the question is, well, do electrons do the same? Will electrons, normally when we think of electrical transport through a copper wire, we imagine the current flowing uniformly across the channel. But if we have one of these systems that's behaving hydrodynamically, what would we expect? And so this is a perfect example of something that this scanning NV center, this quantum sensor, can help us address. So we took graphene and we patterned it. So you can see here the dark lines is the patterned graphene. So namely, graphene is left only in the central channel and these wings here to the right and left. And we're flowing current from the top to the bottom and then letting it extract on the bottom left contact. And the nice thing about our NV center is that it measures magnetic field, and this magnetic field is uniquely connected to the current density inside the material. And it turns out that actually the current density in the Y direction is producing predominantly magnetic field in the X direction, and currents in the X direction are producing magnetic fields in the Y direction. And so by just measuring the magnetic field in space, we can then reconstruct the current density across this channel. And by the way, these experiments are all done at room temperature. And what you can see already is that indeed the current density is going down to 0 at the boundaries and it's peaked at the middle. And if we plot, look at these red dots here, this is the actual one of the cross sections across this channel, you can really see that this current density goes down to 0. It is not an assumption. It is an observation that the current density goes down to 0 and it peaks in the middle. And to contrast this, just to kind of be sure, what we did is we measured a disordered graphene channel. So a low mobility graphene channel, which is the yellow dots, and there you see when the momentum relaxation processes are dominating, you get a flat current profile. And the same happens in a metallic wire where the density of electrons is very high. So this was very encouraging. And we were so encouraged that we said, well, can we find hydrodynamic behavior in a system that actually has a large Fermi surface? And so we went to a material known as tungsten ditelluride. It's a vial semimetal in a bulk form. It has some really interesting properties in monolayer form. It can become a quantum spin Hall insulator. It can become a superconductor. And here again, we were asking, well, okay, suppose we take a channel of this graphene, of this tungsten telluride, what would we expect? Do we expect to see hydrodynamic flow? And when we worked with our collaborator theorists at Harvard, Prerna Narang and her group, what they computed was they showed that the electron-electron scattering rate was really, really small. So it's kind of unlikely that the interaction between electrons would lead to hydrodynamic behavior. But interestingly, they find a different indirect mechanism for electron-electron interaction, which is one electron emitting a phonon, and then another electron absorbing that same phonon, and therefore, again, the energy and momentum remains within the electron system. And this interaction now becomes much longer range. And there, it turns out that the electron-electron mediated by phonons can be quite strong, and the outcome was indeed a hydrodynamic flow. So here you see as a function of temperature, the profiles, they're all quite hydrodynamic, and there is a very interesting temperature dependence that we were able to explain based on this indirect electron-electron scattering rates that involve the exchange of phonons in the process. Okay, in the last 10 minutes or so, what I'd like to do is tell you about something that we're really excited about, and yet again, a different use of our quantum sensor. And this time it's in developing an entirely new scattering platform, a platform to probe material properties, but that uses a very different type of excitation, spin waves, rather than anything else. So just to remind you what a scattering platform is, we are all familiar with neutron scattering, X-ray scattering. The idea is that we have a chunk of material and we have some coherent source of particles or waves. This could be light, it could be neutrons, it could be whatever interests you. And we shine this coherent waves that have a well-defined energy and momentum onto a sample. And the diffraction, the material diffracts these waves. And the nice thing is that we don't really need to measure any property inside the material. We're measuring the properties outside in vacuum. But by measuring the scattered intensity and ideally phase, if we could do both, we could then reconstruct a property of the material precisely. This is how we get structure of crystals. This is how we get magnetization using neutron scattering. These are very, very powerful techniques. You could do it elastically, where there is no energy loss for the incoming waves or particles. They scatter with the same energy, or it could be inelastic scattering. So there's huge variety of scattering experiments. So what we were interested in doing again is addressing some properties of mesoscopic samples, samples where we can't really study them with our conventional scattering approaches. So what we were envisioning is the following setup. Suppose I have a slab, which is some kind of a magnet, that we know how to excite spin waves in this magnet. And suppose we had a way of imaging these spin waves, these scattered waves, and ideally we'd had a way to measure both their amplitude and phase. And I'll show that using our NV centers, we can measure the amplitude and phase of the scattered waves. We don't need standing waves. We can measure the amplitude and phase of the scattering of the propagating waves. We then position a sample of interest on top of this medium. And so what serves the vacuum that was the case here, where these X-rays were propagating in vacuum before impinging on a material, here our vacuum is this magnetic slab. Then these spin waves will interact with the material of interest and then diffract somewhere out to far field. So generally what we need to be able to show is that, number one, we know how to launch coherent waves with well-defined energy and momentum. In fact, that's something that people have done already before us. We need to be able to detect the scattered waves, and ideally, as I mentioned, both amplitude and phase. We'd like to have appreciable interaction between the medium of interest and these waves. So this is going to have to be something that sits on the surface or very close to the surface so that it interacts with these spin waves. And of course, we need to have a reliable way to extract target properties from the scattered waves. And there's a big question here, in fact, what is the quantity that we'll be measuring? Typically, scattering experiments measure something that's called a structure factor. What would be the structure factor associated with scattering spin waves? All right, so just briefly, let me mention that these spin waves, we already encountered them when we talked about the spin chemical potential. Only now we have coherent waves. They're generated by this antenna, which we are sending currents back and forth. This current is generating local magnetic fields that's driving the magnet and produces spin waves at the frequency of the oscillating current, omega. And the wave vector, the momentum of these spin waves, is just selected by the dispersion of the medium. So at any given point here, you see that I have a time-varying magnetic field. And the phase of this time-varying magnetic field is position-dependent. And so it turns out that time-varying magnetic field is precisely what drives our two-level system, our sensor. It drives it from the ground state to the excited state and back. And if we have another signal that's position independent, which is a reference signal, the summation of these two produces a vector whose intensity now will depend on position. And so by simply monitoring the intensity of our NV response, the response of our sensor, as a function of position, we can image in real space the propagation of spin waves. And here you see their wavelength is about 2 or 3 micrometers. But we can really get a real space image of the amplitude and phase of these propagating waves. These are not standing waves. And in fact, we can go down to fairly small wavelengths. At the moment, we went down to 400 nanometers in this publication, but now we're working to go down to about 50 nanometers, which hopefully will be enough in order to approach problems like Are magnets, where the underlying magnetic order length scales is a few tens of nanometers. So how does this experiment look in practice? So we demonstrated this technique by taking a different magnetic material and positioning it on top of the surface. So again, the role of our sensor here is just to image the amplitude and phase of the scattered waves. We need to measure 2 quantities at each given point, the amplitude and the phase. And so we're doing 2 different experiments, one where we don't have our reference signal. And so this is an amplitude map. This is our target here in white. And you can see that in the far field, we're getting some interesting scattering pattern of our intensity. And then when we add the interference, we can extract now the phase of the scattered amplitude. And the question is, okay, what kind of property of the underlying material can we extract by measuring in the far field only, just these signals far away, to say something about the underlying oscillating magnetization as it's responded to the underlying spin waves? So I just want to give a kind of a sense of what we might expect. The underlying magnetization of our target is, let's say, pointing along the X direction here. The fluctuating component of magnetization is therefore going to be pointing in the Y direction. And what the magnetic field that we're measuring turns out to be sensitive to the divergence of the fluctuating magnetization, which means that it's our source, if you like, for the signal that we're seeing is some kind of a dipole that sits on the plus and minus side of this disk. And so we can try to generate the scattering patterns that we're observing just by simulating different sources. So you see here, this is on the left is our measurement. In the middle is just a dipole. And you see that it's not doing a very good job at producing our target. So we can go to the next moment. So we're adding a quadrupole, and now we're getting better. And this process can, in principle, continue more and more until we really get what the underlying fluctuating scattering source that scatters our spin waves. So this is, this is a direction that I'm particularly excited about right now, because I think it will really provide a new way of looking at materials. And again, the enabler here was our ability to image both amplitude and phase using this new measurement technique of the scanning NV center. So with this, I'd like to basically just kind of summarize and give a short outlook. As I mentioned, I've been convinced for many years that progress in the understanding of materials is a cyclic process between the development of new measurement capabilities and then applying these measurement capabilities to study materials. Sometimes we discover interesting properties in these materials that allow us to develop yet new measurement capabilities, and the cycle goes on and on. And so for the students in the crowd, I really encourage you to think about not only the physics that you want to extract, but how can you extract it and come up with new ways of probing materials. I think this is a really fun area to work in. And with this, let me just acknowledge the group, the people who have really done all this work, and stop here and take some questions.
Thank you very much, Amir. It was a very clear and very interesting talk. So, wow. The colloquium is open to questions.